All right, so last week we introduced trees and the basic terminology and justified that we could exploit this data structure if we stored data in it because it was very similar to a binary search kind of idea where if you start at the top, you can look if that's what you're looking for, great. Otherwise, you can basically split the tree in half and all of your operations, putting stuff in, taking stuff out, searching things, if they can be made to be proportional to the depth and the depth can be made to be logarithmic, then of course we've achieved our goal of efficient operations for everything. Then we briefly previewed what an implementation might look like, and that's where I want to pick it up today. So we're going to go ahead and go over here to Eclipse, and we're going to start by creating our first tree node, and I'll call it binary tree node. There we go. And what's in this binary tree node? Remember that we are online, so if you have any questions, go ahead and post to the live stream here. Otherwise, what we've got is an element because we're ultimately going to store data. So I'll go ahead and make this into a private final element of type T, and I'll just call this the element that we're storing here. Okay. And then, of course, we're going to need references. And if we've got a tree, then each node here is going to have a reference to possibly its left child or right child. If it doesn't have a reference to it, in other words, it's going to be null. Right? And so we're going to want a left child and a right child here, which is private. I won't make this final because I do want to set them later on. We want to maybe reconfigure the tree somehow. But otherwise, this is going to be a binary tree node of the same type, and we've got a left child. Right? And then we've got a binary tree node of, again, the same type, and we've got a right child. We also observed that it would probably be useful if we can have back references up to the parent. This is very, very similar to like a doubly linked list where you can go from one direction to the other direction and then back again. Okay? So I'm just going to simply generate all of the getters and setters here. Right? Select all. There we go. All right. So that we can actually have something to work with here. And also I'm going to go ahead and create a default constructor, not a default constructor here, but I'll go ahead and create a constructor that is just based on the element here. In other words, we're going to be able to reconfigure this thing so that you can reset the parent, you can reset the left child, the right child, so you can reconfigure the tree. Okay? Once we've got a tree node, how do we represent a tree? So, yeah, go ahead. From the head, or that there's a special name for that. It's not the head of a list because there is no beginning, there's no end. There are many ends, right? There are many leaves here. This guy up here is called the root. And that's all we're going to keep track of. Because if we keep track of every single node, then it's no better than going back to a list. So, private, I won't make this final, but I will make it into a binary tree node of some type, and I'll call it the root. Right? There we go. And that's it. Okay? So what we need to do now is we need to start designing around this thing. So for example, I'm going to want to eventually put stuff into this tree. I'm going to eventually want to find stuff in this tree. I'm going to want to eventually remove stuff from this tree. So as my first method here, let's go ahead and make it into a public method, void, add new root, element of type X here. There we go. Now, let's think about that for a second. Here's this data structure that holds stuff. By now, we've seen several of these. It could be an array list. It could be a linked list. It now could be a tree. Do we want to have to worry about that basic structure under the hood? No, that's the point of abstraction. I just want to add something. So adding as a new root, that kind of leaks information to the outside world. This is a leaky abstraction. I simply want to have insert. You put it where it belongs, right? You're the tree. You should know, right? This is the correct abstraction. I don't want to have to worry about those low-level details. And if I say insert at end, right? Insert at as root, et cetera, I am leaking information to the outside world. In fact, does insert at end even make sense for a tree? No. Right? So I'm going to keep it as a generic insert method here. Other things that we might want are public, void, I don't know, or element t find, right? Some element t x, but if you've already got it, how does that work? Right? If you've already got it, how do you, if you've already got x, how are you going to find it? You've already got it, right? We'll come back to that, right? I want to bring this, I want to highlight this to your attention because as you're designing your list data structures, your sorted list data structures, keep that in mind, leaky abstractions. For example, insert at index, right? Int index. Now in the context of a tree, does it make sense to talk about indices? No. In the context of a list, it does though. But in the context of a sorted list, does it make sense that you should be able to arbitrarily insert anything you want wherever you want? Probably not. Because that would not be a sorted list. Here's a sorted list, 10, 20, 30, and 40. You want to insert 42. If you're allowed to insert it at the beginning, is that sorted? If you're allowed to insert it at an arbitrary location, is that sorted? Nope. So, when we say insert, we simply mean, hey list, you're a sorted list, you know what you're doing. Here you go, here's 42, you insert it where it needs to be. Make sure that that's a proper abstraction, not a leaky abstraction, and not an abstraction that breaks the semantics of what you're trying to do. So let's go ahead and revert this back to insert, okay? How are we gonna get stuff in? I don't know yet, right? So what I've done is I've come over here, oh, it's not compiling, darn it, why not? Let's see. Binary tree. Oh, okay. Let me go ahead and modify this so that we actually have a constructor. Public binary tree, and we'll take in a binary tree root. T root. There we go. And then this dot root root is equal to root. There we go. All right. Now it should compile over here. Great, it does. Except for what's wrong. Oops, got the wrong package declaration, uno.ece. There we go. All right, great. So what I've done over here is I've manually built a tree. I've built a tree with nodes A through R, A, B, C, D, E, all the way through R. And then I went ahead and set all the left children, all the right children, all the parents of each and every single one of these nodes. In other words, I made, this tree right here. Okay? We're going to be playing with this tree a lot here. But I've also created another smaller tree, right, that has A, B, C, D, E, F right here that looks something like, ooh, do I have it? I don't know if I have it or not. Let's go ahead and get rid of this. Do I have the small binary tree? Yep, there we go. Here's a small binary tree. Okay. And we're going to start out with that, and then eventually we're going to work our way up to that larger tree. Because I don't know how to get stuff in there yet. Right, let's go back to the binary tree. This one's done. Right. I don't know how to get stuff in there. Where are you going to put it? Right? Well, there are lots of places that I could put it. I can't put it right here. Right? I could put it right here. I could put it right here. I could put it as a left child or right child of D, left child or right child of E, et cetera, et cetera. Where's the best place to put it? I'm going to leave that off for a second. Okay. We've got our implementation in Java, C Java code. Right? Now let's think about operations. Right? So yes, getting stuff in there is the first step, but I'm going to hold off to later. Right? What about retrieval? Right? Remember CRUD, create, retrieve, update, and destroy. Let's go ahead and suppose that we already have these trees built. That's exactly why I did this over here. Right? There's a small tree and a big tree. Now let's go ahead and think about retrieval methods. Okay? For this, we're going to have to think about traversal strategies. With a linked list, you started at the head and you worked one way because there was only one choice. Or you could start at the tail and work backwards. But with a tree, is there a defined starting point? Yes. The defined starting point is always going to be the root because that's all we have access to. But from the root, oh wow, do I go left or do I go right? Well, if you're exploring it and you're trying to find, say, F, and you go left, are you going to find it over here? No. If you're exploring and you're trying to find D and you go over here first, are you going to find it? No. So eventually what you have to do is you have to go left and then right if you don't find what you're looking for. Right? Which order do we go in? Left first? Okay, left first. And then eventually we'll have to come back over here to right. Right? So I found what I processed what, is this what I'm looking for? I'm looking for A. No? Okay. I'm looking for E. Right? Nope. So that's not what I'm looking for. So let's go down over here. Is this what I'm looking for? I'm looking, again, search for E here for a second. Right? So that's not it. Go to left. Is that it? Nope. All right, so continue that same strategy. Go left again. Is that it? Nope. All right, now what do you need to do?
No left child, so go right.
Yep, oh, okay, yeah, no left child, no right child. So I need to start backtracking. Right? And when I come back up here, I see that I've already processed B. In other words, I've already looked at it and said, that's not the thing I'm looking for. And so where do I go next?
Right.
I go right and find what I'm looking for, and I'm done. Right? If I were searching not for E, but for F, right, I would have searched this entire subtree. Nope, nope, nope. Come back up here. I already searched A. Now go over here. Nope. Oh, there's no left child over here, so I go to the right child and I find it. And there, it's successful now, right? That's what's known as a pre-order traversal. Let's think about it in more general terms here. If I'm at a current node U, right, I came ostensibly, right, from a parent node, P up here, okay? I might have a left child, I might have a right child. Right? If I don't have those children, then I can easily say, okay, we'll skip it, right? Because there's obviously, if there's no left child, then there's no tree hanging off of that left child, okay? A pre-order traversal is going to take the following strategy. It's going to process the current node, and by process I mean if you're looking for a needle in a haystack, you're going to compare it. If you wanted to print it out, then you're going to print it, right? Whatever process means for you. Right? Then you're going to traverse left, and then you're going to traverse right. Right? The problem is, how do you know? Okay, so I'm at this node right here. Right? I've already processed it maybe. Maybe I've already come down over here and explored the entire left subtree. How do I know that? How do I keep track of where I've been? Right? So you need to be Hansel and Gretel, right? I came here, I went down there, I came back over here, and then I need to go down over there. So I need breadcrumbs to say, you've already looked at this one, you've already looked at this one, somehow. Right? So how did Hansel and Gretel set their breadcrumbs? Right? And then they want to reverse it. Well, if you set 5 breadcrumbs, 1, 2, 3, 4, 5, and you want to reverse it, which one should you look at first? The last one. Oh yeah, 1, 2, 3, 4, 5, the last one that you put in. So the last one that you put on the ground is the first one that you backtrack to. What does that sound like? Yep, it's a stack, exactly. Right? So let's think about this more generally here. All right, let's actually simulate it with this small example first. All right. So if I'm going to go root, remember this is pre-order traversal. So I'm going to go root or current, then left, then right. This is my traversal strategy. Okay. So I'm going to go ahead and look at A. I'm going to start at A here. Right? There we go. And so I'm going to process it. And then eventually I'm going to go to the left subtree and then to the right subtree. Right? How do I need to remember that I still need to go over there? I'm going to create a stack and I'm going to put stuff in it. Right, there we go. So actually, let me backtrack just a little bit more. How do I get this entire thing started? I'm going to put A down here at the bottom of the stack. Then I'm going to pop it off. All right, and so here's my current node. All right, and once I've popped it off, it's empty. I look, and so I'm at this current node. I process it, U. All right, so process order. There we go. I'm going to process, not U, sorry, but A. There we go. And now what I'm going to do is I'm going to look at its children. Which order do I want to go in? Right? Now remember, I'm going to go left first and then right. But because this is LIFO, which one do I want to push into the stack first? A has already been pushed and now it's out, right? So let's put C and then B. Now why do I do that? Because the next time I pop something off, I'm going to go to B. Right? I'm saving C for later processing. So I'm going to push right, push left, and then iterate. Right? So now I'm going to pop off what's on the top of the stack, which is B. Right? Oops, B. I will process B, and then I will look at its children. I will push its right child, and then push its left child. Okay? Next iteration here, I will pop off the top. D. And we end up with D right here. I look at its children. There is no right child, so don't push it. There is no left child, so don't push it. And guess what? We've essentially backtracked to B here, having already processed it and its left child. Now, when I pop, I have E. And I process it. I didn't miss it because I put it in the stack at some point. Now what do? I pop off the next one. And guess what was there? C, the thing that I need to process after processing this entire left subtree here. I look at its right child and push it, F. I look then see that there is no left child, so I end up not pushing it. And remember that I did already process it, C. There we go. And on the next iteration, I pop, and I've got F. I process it. I see that it has no right child, no left child, and I'm done. By what criteria do you know you're done? Nothing in the stack. Nothing left to explore. So let's do that on a larger example here, right? And we'll speed run this, right? So clearly I'm going to process A first. Right? Then I come down here to the left subtree, right? And now I'm currently on, let me go ahead and, I've processed that. I come down here, I process B. I come down here, I process D. Right? And you can start to see the pattern here, G, L. Okay, what's next? M, then R, right? Good. Then what? H, N, good. Right? And then by now I've come back all the way up to B here, and so I go down and traverse right. E, there is no left tree, and so I process I, O, E-I-O. Okay? Now what? I'm way at the top again. So I traverse down here. C, nothing down here, so I go over to F. C, F, J, P. Why? Because the same pattern. You traverse left until you can go no further. You are going down a maze, basically. You go down until you find a dead end. Then you backtrack and you try something else. So Q. Then I already have F somewhere. Yeah, F. Then K. There we go. That's a pre-order traversal of this graph, of this tree. Here's my tree over here, the small one, and here's my big one. Let's go ahead and implement this pre-order traversal. For now, I'm just going to go ahead and print them out, but then we'll go ahead and redesign this. So, public, I don't know, void print pre-order. There we go. All right. So, let's think about this. Let's go back over here. Let's go back to the small example that I had over here. And let's outline this in pseudocode first. The first thing I'm going to do is I need a stack. So here's my empty stack. Right. Now how did I get this entire thing started? I started at the root and I pushed it. Right. So push, or s dot push the root. And then, there we go. All right.
Would you consider that pseudocode still? Or
Sure.
should that stop?
Yeah, I'm just outlining it anyway, right? If you wanted to, you could go ahead and alternatively say, push root onto s.
Okay, S dot push, that's better.
Yeah. It's getting less pseudocodey because, of course, you've got the indirect component selection operator, or the direct component selection operator, but whatever, right? Okay. Now what? I need to go into some sort of a loop, right? There's stuff on top of the stack here. I'm going to pop it off, I'm going to process it, and then I'm going to push to the right child and then the left child. Right? So what kind of a loop do you want to do here? Do you know how many iterations you're going to do up front?
No.
No, I don't either. So let's go ahead and go with a while loop. And what's the criteria that we observed? When did we stop? When the stack was empty. Right. So while s is not empty, I'll do the following. I will pop off the top, s.pop. Is that pseudocodey or not? I don't know, who cares? Right. And then I will push let's go ahead and process it first. Process x, right? And then I will push x's right child, and then push x's left child. There. Now, what do I mean by process? I mean print, at least for us, right? For now. Okay. So just 4 steps here after the initialization. Let's go ahead and create an empty stack first of all. Stack that is going to hold binary tree nodes. There we go. S is equal to new. Ooh, how do I do stacks? Linked list. There we go. Why? Because we can work at one end, we can work at the other end, right? Remember that we called these things more generally, we called them decks. Right? What are you complaining about? Why can't you infer that? Fine. Oh no. Oh, well, no, you can. Okay. Why can't you figure this out? Not infer type for linked list. We have a linked list up here, right? Yeah, we do. I'm not sure why it's not. Oh, because it can't change this into a stack. Why? What are the? It is a class. Oh, okay. It's just a class. Stack. There we go. Let's go ahead and take a look at it. It's a subclass of vector. I believe that this is here because of some legacy stuff. In fact, yeah, since Java 1, stack existed, it's much better to use a deck, an array deck or a linked list. Any case, this is fine. This is good enough for us. Right? There is my new stack, right? And what's the first thing I do? S.push this dot root. Right? There's my pseudocode. I push the root onto S. Then I go into a while loop. While S dot is empty, while it's not empty, right? Then I will keep processing. Right? So here's my binary binary tree node, excuse me. Right? X is equal to S dot pop. Right? That's the first line here. The next line is going to be to process whatever's stored in that node. Right? So process is just going to be system.out.println x.getElement. Right? Remember, I don't want to print out the actual node. I want to print out what is stored in the node. And then I need to push its right child, push its left child, if they exist. S.push x.getRightChild and S.push x.getLeftChild. There. Now, do we want to be pushing null? Probably not. So I will add some additional checks here that are not in my pseudocode. X dot get left child is not equal to null. Then, and only then, will I push it. There we go. And if x dot get right child is not equal to null, then and only then will I push it. Oops, I'm backwards here, sorry. Left child, right child, there we go. Right and then left. This did not appear in my pseudocode, did it? Why? Because I assumed that you could make that leap, right? That they're going to, that the pseudocode is going to assume that when you translate this to an actual programming language, that you're going to make those considerations at that point, right? I didn't put in an additional if x has a right child, then push the right child. I just left that to your own devices with respect to the pseudocode. All right. So first of all, let's go ahead and get that simple tree, right? That small tree, tree utils. So tree utils dot is equal to that, and then we'll go ahead and say t dot print preorder. There we go. Now, if this works, we've already worked out what it should be. What was it before? Right here. A, B, D, E, F, C, F. And so if we've implemented this correctly, we should have that exact same ordering. A, B, D, E, C, F. Looks like it works to me. Right. Let's go ahead and try it with that large tree. Run this. And I see A, B, D, G, L, M. A, B, D, G, L, M. Right? And what's the rest of it here? I'll just scroll over here. The last one is K, Q, P, J, F, C, O. It looks good enough to me. I'm pretty sure it works. Now let's come back over here and rethink this design a little bit. Instead of just printing things out, maybe we could do something else. Maybe instead of printing it out, we could give you a list of elements of type T as a preordering. So what I'll do is I'll create this, let's go with a list of whatever, array list, linked list, doesn't matter. Result is equal to new array list. Now, instead of processing it by printing it out, where is that? Here, right here. Here, my process is going to simply be result.add x.getElement. Right? And then ultimately I'm going to return that result. There. Import this. Now, is this a little bit better design or worse design or just the same? Instead of printing it out, right, which just dumps it to the standard output, I can now have access to it. Now I can print it out or I can do something else with it. Preorder is equal to t dot get, or what was it, dot pre-order? There we go. This is a little bit more flexible design, right? Because you're giving me a list now, and I can do with it whatever I want to do with it. Right? How could we go even further? Let me try something like this. Usually with a list, what I could do is something like for string s in the collection pre-order. Right? And I can go system.out.println lns. There we go. And this will work perfectly fine, just as we did before. Okay? What if I didn't want to do that on this list right here? What if I wanted to do that on the tree itself? Can I do that? Oh, is it compiling?
Well, no.
No. I really want to do that though, right? I want to treat my tree just like a list or any other collection, a set, a hash set, whatever. I just want to iterate over it in this nice enhanced for loop. How do I do that?
Interface?
An interface, okay. What kind of an interface?
Not sure what I would name it, or not sure what it's
Implements,
first iterable?
iterable, exactly. There we go. Elements of type T. There we go. Now it's going to complain because of course we need to add that unimplemented methods. There are several, okay? Actually it's just the iterator. There we go. All right. So we're going to give them a new iterator. An iterator for elements of type T. In this particular case, it's going to be for strings. What does this look like? Return a new iterator for elements of type T, and I will immediately define it in line here, okay? Add those unimplemented methods. This is going to have actually 3 of them, right? Oops, no, 2 of them, sorry. Say again? All right, so what are we doing here? We made our class iterable so that we could put it into a enhanced for loop so we don't have to dump it to a list every single time. We made it so that we could iterate over the elements in this tree. How did we do that over here? I iterated over elements in this tree by going to the first one, processing it, then to the next one, processing it, then the next one, then over here, then over here, then over here. Right? All I'm doing is instead of dumping that to a list, is I'm making my class iterable itself. Now, how does that done in Java? Let's go ahead and get rid of this now. Right? Go over here. I implement the iterable interface. I'm going to iterate over elements of type T, strings. Right? That means I need to return this thing called an iterator. This iterator is a black box that you ask questions of it. You ask questions like, do you have another one to give me? And it says yes or no. Do you, okay, fine, give me the next one. Okay, here you go, here's the next one. At some point, it's going to say, no, I don't have any more, right? And then you're going to be breaking out of this enhanced for loop here. So how do we do this with a pre-ordered traversal? Right. Do we have a next? What is the next? Right. Well, I'm going to take this pre-order algorithm that we just established, and I am going to translate it over here in my object. So first of all, we've got a stack. And actually, let me make this into the constructor is what I'm looking for. There we go. Public iterator, right, for elements of type T. Right, there we go. There's our constructor. Actually, no, we don't need to do this. We don't need to do this in the constructor. What I do need to do in the constructor, though, is s.push, that first initial result there. So I don't think I can do that out here. No, I cannot. All right, so we are going to have to do this in a constructor, or at least this part in a constructor. Public iterator, elements of type. I don't know if I have to parameterize it. Nope, no parameterization. Uh-oh. Ah, darn it, how do I do this? Bear with me for a second. pretty sure I did this before. Nope, okay. Darn it. Yeah, I don't know, I don't want to put this into its own class, is what I'm thinking.
Is that what like this nested thing is essentially?
Yeah, and that's what this is doing. So I'm going to give you a new iterator here. I could save this off. Iterator t foo is equal to this. And then I could say that, no, I can't treat it like an iterator. Darn it. I'm pretty sure that there's a way of doing this. Control Z. Set methods, okay, yeah. That's not correct though, because I need a constructor, but this is going to be, how do you do this in Java? All right, we're just gonna have to do it over here, right? No, I still need a flag value. Dot push, fine. Root. Nope, that's not gonna return that, the list. All right, I can't do it there either. Darn it. Okay. Then let's take a digression here. Anonymous Java class constructor syntax. Anonymous classes in Java, accessing the constructor of an anonymous class. No, that's not what I want. All right, fine. Java iterable constructor. Iterator. Anonymous iterator. Yes, you can. All right. All right, fine. I'll do it the hard way. I'm sure that there's another easier way of doing this, but doing it the hard way means that I'm going to do a new class, which is a binary tree iterator. There we go. Finish that. And it implements iterator. Implements iterator. There we go. Bring that in, import that. And then we need to add those unimplemented methods here. And now I can have a constructor because it's no longer anonymous. It has a name, binary tree iterator. Right? And this one will have what I need over here, which is a stack. And I can initialize that just right here, private final stack. And then in my constructor here, I can say s.push. Tree, no, you know what? Now I'm outside of the, all right, fine. Get rid of this. Oh man, I'm stumped. I've done this like a million times. I can't believe this is a brain fart here of how to do this. Private, of course. This is the constructor, so I can't define the constructor. So s.push, can I just do that? Probably. This dot, or not this, but root. Nope. Darn it. All right. Anyway, do you have another one? That means that you're going to look at if s dot is empty, right? This this logic up here. If it's not empty, then we'll go ahead and say, return that. Yes, I do have another one to give you. It's in the stack. Right? The next here, what this is going to do is it's going to take this logic right here. Right? You're going to pop it out. You're not going to print it or add it to a list. You're going to eventually return it. Right? And so, but before you do that, make sure that you are pushing the left child, pushing the right child, and then return the actual element there. Right? Darn it, how do I get that first guy in there? There's got to be, well, okay. Add a return state. Oh, that's because I'm not doing that. Okay, there we go. Man, there's got to be, let me put in a to-do here. I'm not going to waste any more time on this. Need to push this tree's node first, ... We'll come back to that, right? Okay. Anyway, it still works because I'm going to have this list data structure here instead, and then we'll change this back to a pre-order. What I want to do with the rest of our time is look at alternative traversal strategies, okay? So let's go ahead and come back to this small example here, and let's think of other ways that we could have done this. Right? So the way that I did this with pre-order was that I processed the root node, then I went left, then I went right. Okay? Now I am going to still go left and then right, because why? You could just go ahead and transverse the tree, right? If I went right first, I could just take the tree and then flip it around, and I'm doing the exact same thing. So what I want to do is I want to consider a different order of processing. A left, then a root, then a right. Okay? In other words, the only difference here is when you process the root. Do you process it before the left and right, or you go left and then you go root and then you go right? Right? That's called an in order, and eventually we'll understand why. In order traversal strategy. Okay? Again, I'm not going to flip left and right because I can just flip the tree, but what's another strategy that I could have done? Left, right, root. Right? And that's going to be a post-order traversal strategy. Right? Okay, so no, why? Pre, before, post, after, in between. All right, let's go ahead and look at this small example here and do it with a left, root, right. So when I start out at A, I do not process A first. I do the left subtree first, then I process A, then I do the right subtree next. So I come down here, I don't process it, I go left. Do I process B? Nope, I process the left subtree first. Come down here, do I process D? Technically no. I look and see that there is no left child, and then I process D. Then I see that there's no right child. So with an in-order traversal, the first thing I end up processing is D. Then I come back up, and now I've done the entire left subtree, so now I process B. Then I go down and process the right subtree, E. Having done this entire subtree, I now come back up, and now I process A. Then I go down to the right subtree. Do I immediately process C? Technically no. Again, I look to see that there's no left child, and then I process C. And finally F. Okay. One observation I want to make. Where's A here? Right in the center. Everything over here is in the left subtree, everything over here is in the right subtree. What was it in the pre-order? Pre-order was what? Let's go ahead and reproduce that. It was A, B, D, E, C, F. Where is it in the pre-order traversal? Right at the beginning. Where do you think A will be the root of the tree in a post-order traversal? Right, exactly, post-order. So what's the post-order look like? We start out here at A, but we don't process it. we go left first. We don't process it, we go left first. We end up processing D because it has no left child, no right child. So D ends up being first. We come back up, but we do not process B yet. We go down to E first and process that. Then we come back up and process B. We don't process A because we already observed that it's going to be last. So we come back over here to C, right? There is no left child. We don't process C. We go to its right child, F, and then we process C and finally A. And once again, we observe that that root is going to be at the end. Okay. Do we want to do it over here too?
No.
No? Okay. Then let's come over here and implement those. That's fine for now. Right. I'm going to go ahead and, because I couldn't get my iterator working just yet, we'll do that some other time. Right. I'm going to go ahead and make this into an in-order traversal, and we're also going to want to have a post-order traversal. Right. Now I could do this stack-based. In fact, I'll show it to you here in a second. But what I'm going to do is I'm going to go with a different strategy here. I'm going to think about this recursively, right? Recursion. Remember that bad thing that if you can avoid it, you do, right? And if you can avoid it, I would suggest that you avoid it here as well. But let's think about it, okay? I'm at a current node U, right? I came from my parent. How do I know where I came from my parent? Well, in the previous example, we used a stack to keep track of our breadcrumbs. Now we're going to abuse the call stack to keep track of where we came from. When I return, I will return back to the parent. Right? So how do I make sure that I go left and go right? So if I've got a, say, in order, then I'm going to have a current node. And I'm going to call it U because that's what I've done over here in this picture right here. So if I do this recursively, I will want to go left and then I will want to go right. So in order on U's left child, if it exists, of course, I'm just outlining it now, and in order on U's right child. Now, where do you process U? If you process it right here, would that be an in-order traversal? Nope, you're going to U and then left and then right. So where do I put process U?
You think I had to leave space for it?
Exactly, process U right here. You go and recurse left. Once you've come back, then you process it, then you go right. Cut and paste this. How could I have done an in-order traversal of this instead? Put it right there. How do you think we're going to do a post-order traversal strategy here? Put it right there. So in this case, recursion seems really, really nice because all I have to do is change one line of code and I get a completely different traversal strategy. Right? Seems, yeah. Right? You're abusing the call stack now. Right? And if you've got a very, very deep tree, it would have to be massive, but you would end up getting a stack overflow eventually. Right? All right, so let's do an in-order traversal here. If you remember, on your sorting lab, we actually had a quick sort, and then we told you, go ahead and make a recursive quick sort. Why? Because you needed a main entry point here, a non-recursive entry point. Because eventually you're going to have a public void, I'll make it a void here, not public either, private, void, in order, that you have a current tree node, binary tree node, T, current, right? And also this list that you're passing back and forth so that you can append it, append it, append it. Right? Result. There. Binary tree node, there we go. Right? Now an in-order traversal strategy is going to be if the left child exists, recurse on it, right? Then process the current node. Then if the right child exists, recurse on it, dot, 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 or dot, 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 right? Remember, we're going to have to think about this recursively though. Up here, I'm going to go ahead and create a list of elements of type T. Result is equal to new array list. There we go. Again, this is my non-recursive entry point. All I'm doing is setting stuff up and then calling that initial recursion in order on this dot root and the result. And then return the result. I'm passing this list down the call stack so that it can add things to the end of the list. All right, how do we take care of this? With recursion, what's the very first thing you should always do? End the recursion. When do I stop? This is going to be my base case. If the current node is invalid, don't do anything. So if current, how do I know if it's invalid or not? If it is null, just simply return, don't do anything. Otherwise, if the left child exists, then recurse on it. Otherwise, and then process the current node, and then if the right child exists, recurse on it. So the recursion here would end up being current dot get left child, and then the same result here. Right? And this one would be get the right child, and then recurse on it.
So you don't do the check in that line of code, you just have the if current equals null.
Good
and
observation,
one step down.
right? Good observation. I could have the check here if, current dot get left child is not equal to null, then recurse on it, in which case I actually wouldn't need this base case. Right? But I'm going to go ahead and pass you null so that you don't do anything and you immediately come back. Which one is better? I don't know. You're doing the check down there or you're doing the check up there. Right? Simpler code is better, right? So I'd argue this. Right? Now we do need to process it, of course, so result.add the current node dot get element. There we go. And we know that it's not going to be null because we would have returned already. There. Let me go ahead and get rid of this for a second so that we can test this in isolation. Right. And this is going to be a in order, and it'll be t dot in order. There we go. Let's go ahead and go with that small tree.
Go big or go home.
Well, we didn't do it, remember? I don't know what it is. So let's come back over here, and an in-order traversal was going to be DBE, here. DBE ACF. Looks good to me. Now, what you would want to do is you would want to repeat that on an in-order traversal here. We could do a little bit, without doing it fully, we could do a little bit of a sanity check here. Large tree. Let's go ahead and output this.
Stack smashing it.
Where would A be?
Right?
Right in the middle before
Little
all this
right.
stuff, right? So, L is going to be first, and then we've got G, and then R, M. Look, the first few of them look good. All right, A looks right where it needs to be. And then there's everything on the right side of A. Undo, undo. Let's come over here and do a post-order traversal, but again, I'm going to use recursion instead. All right, so let's get it kicked off by calling a recursive version of post order. And I'm going to just cut and paste it. Really bad practice here, but I'm going to show you that it is virtually the same. The only difference is going to be post order here, post order, and the only difference is where you put this one line of code. You add it at the end. So, post order, and post order. There we go. And again, sanity check here. Well, here, we can actually do this one, right? It was DEB FCA. Good. And then we can do a sanity check here and make sure that A ends up at the end with the large tree. Because you didn't want to do it, huh? Right, there we go. At least it is. All right, we've only got 5 minutes left. Let's get rid of that evil recursion. We're not going to be able to do it in 5 minutes, but I'm going to show you what it looks like if you do. Here's from the Computer Science 2 textbook. There's pre-order traversal. There is a stack-based in-order traversal. The key idea here is that you just need to distinguish whether or not you're coming back from the left child, in which case you process the node, right here, or this is the first time you've visited the current node, and then you need to go right, waiting on processing the current node until later. And for that, you just need to keep track of a previous, the current you here, and I guess you don't need to keep track of a previous. You just need to keep track of where you've been, right? Yep. You left your child, exactly, right? So what about a post-order traversal strategy? A post-order traversal strategy with a stack is going to be a little bit more complicated because you need to keep track of the current and determine whether or not, is this the first time I've visited this current node, or the second time I've visited the current node, or the third time I've visited the current node, in which case I process it. So it's just going to be a way more complicated bunch of if-else-if statements. Or you can break it down and not have to use a stack at all. Think of it like this. I'm at the current node here. Here's my parent, here's my left child, and here's my right child. I just simply need to keep track of the current, which is you, and where I've been. So let me move this down. And if I kept track of a previous, if that was a situation, then what does that tell me? I just came from my parent. Where do I go next? Go left, right? And then update, right? Update. The current will end up being the left. And then the previous, where did you come from? From you. Right. What if it were a different situation? This is case 1. Case 2. What if the current node is U, and the previous one is L? What does that mean? Yep, you're headed back up. So where do we go now? To R. Right? What's the third? The current, of course, is still U, and the previous is now R. So that means that you just came from there. So where do you go next?
P to whatever else.
Go back to your parent. Right? Now, where do you process each one of these nodes for in-order, post-order, or pre-order? If you process it, if you process here, then it's pre-order. If you process here, then it's in order. If you process here, it's post-order. In other words, you don't need to keep track of anything, right? All except for the previous and where you are. Where you've been just immediately came from, and where you are right now. What does that look like with respect to our tree over here? Let's do it with the big tree. Let me go ahead and switch this to red. Right? Come down over here, come down over here, come down over here, come down over here. At which point we're done, and so we traverse back up, traverse back down. And now I'm not going to draw arrows anymore. What I'm going to do is I'm going to draw where I'm going. There. So what are you doing? You're just doing a tree traversal. If this is a building, don't think of it as a maze anymore. I mean, you can think of it as a maze, but think of it as a building. How do you go around the building? Stick your hand on the wall and start walking until you get back to where you came from. In fact, that's how you solve a maze, right? If it's completely dark and you don't know where you are, you don't have any breadcrumbs. How do you solve the maze? Stick one hand on the wall and just keep walking, right? Eventually you'll go around corners, around. Eventually you will get back to the beginning. Well, yes. Well, yeah, if it's not static and it's moving around, then you're kind of screwed. Also, that it doesn't have traps or anything like that. But you can solve a maze by simply just going across all the walls, right, without any additional information at all. So that's the blind man's way of solving the maze, right? Just put one hand on the wall. Don't put, be consistent. You can put the right hand on the wall and go around it the other way, just as long as you're consistent about it. Here is another way of looking at it. So we put data into this, and you can see that I immediately put A, B, C, D, E, F, G, right, in order. How? Or why did I do that? Because I read top to bottom, left to right. What if we traverse the tree like that? In other words, once we got done with one row, we came down here to the next row. Once we got done with the other row, we came down here to the next one. The next one, the next one, the next one.
Sounds inefficient.
We'll talk about efficiency next time, but it's just as efficient as the other one. Right? So what kind of traversal strategy would work with that? Note there that I drew one big long line. Line. What's another word for a line? A what? A row? What's another word for a row? Like if you stand in line waiting for something. A queue. Exactly, you queue up, right? How's this going to work? Here's my queue. Oh, okay. Here's my nicer queue. Right? I'm going to start with A. Right? I'm going to put stuff in here, and I'm going to take stuff out of here. Right? What do I put in next in order to ensure that I go top to bottom, left to right? A's left child, B, then B's right child. C. Well, sorry, what did I say? A's left child and then A's right child. Right? Now what comes out? Now I've got B. Right? And so what am I going to put in there? B's left child, then B's right child, which is D and E. You start seeing a pattern here? I wonder, could we do that in, say, 2 minutes? Yeah, we'll do it like this though. All right. I'm not going to call this pre-order, post-order, or in-order traversal because it's not. It's what's called a BFS, or breadth first search. All right. Why is it called breadth first search? If you start at A, then you're searching things that are a distance 1 away, then a distance 2 away, then a distance 3 away. You are doing a breadth kind of exploration of this. Whereas the other one was called a depth first search. You go as deep in the maze as you can before backtracking, and then go as deep somewhere else as you can before backtracking. This, we're not going to do that. We're going to look at everything that's within 10 feet of us, then 20 feet of us, then 30 feet of us. Right? All right. So instead of a stack, what are you going to want? A queue. There is no queue in Java. It's a deck. And a linked list is an implementation of that thing. I'm going to go ahead and call it queue too, to remind myself that it is in fact a queue.
Shouldn't you have refactored it
Oh, what do you mean?
so you didn't have to replace every instance of S?
Oh no, because this is. I could have done that, but I want to remind myself of every single change down the line here. Right? So instead of pushing, what are we going to do? S dot. How do we put stuff into a queue? Offer. Right? Sorry, not S, queue. Right? While the queue is not empty, we will take something out of it. Queue dot, the opposite of offer is take or pull. Right? Then I will add that element. Now remember with LIFO, we went right child first, then left child, so that the right child would be below. That's not the correct order. The correct order here is going to be left and then right, because we want to go top to bottom, left to right. And we're not going to push it, we're going to offer it. Oops. Offer. We're not going to push it, we're going to offer it. Let's come back over here and see if that's all we had to do. There's the, I'll do the large tree here. And this was Brett first search. And I'll rename this BFS. BFS. Did I not call it Brett first search? Public.
Misspelled.
Brett. Breadth. Okay, there we go. I thought you meant I misspelled breadth. No, I didn't. I misspelled search. The even easier one. Right, there we go. All right. So, how do I know that that's correct?
Because it's alphabetical.
A, B, C, D, E, F, exactly. All right. Compare those two. Breadth first search versus a pre-order traversal. What's the only difference?
The action.
Yeah, the data structure that you use. And then, of course, swapping out left and right. Some small little change in the data structure that you use can lead to a drastically different results, right? And this is why smart data structures and dumb code are a lot better than the other way around. Right? That goes all the way back to the beginning of the semester. That's the theme of this course, right? That if you use a stack versus a queue, right, you get two widely different behaviors out of your algorithm. But they're the same thing. You put stuff in, you take stuff out. You put stuff in, you take stuff out. Right? And it's the data structure that is doing all the heavy lifting for you. Right? Deck versus, or queue versus a stack. All right. I'm going to work on that. We will come back to the iterator on Thursday, and I'll fix it. Right. Again, I've got my to-do here. Right. All right. Any questions? Nothing online? Oh, nobody watching except for me.